So our first presentation is a design exploration framework for secure IoT systems. And Lukas is going to present to us. So Lukas, whenever you're ready, I'll hand over to you.
Okay. So hello, everyone. My name is Lukas Gressl. And today I want to present you our work on design space exploration framework for secure IoT systems. I'm a PhD student at the Technical University in Graz, and I'm doing my research together with NXP Semiconductors and CISC Semiconductor at the Institute of Technical Informatics. And our research project was funded by the Austrian Research Promotion Agency. So why is it important to include security aspects at the very first design phase of embedded systems? Because first of all, the late introduction of security measures into already existing systems is very costly and inefficiently. And second, because popped on security mechanisms are often not feasible to mitigate security attacks in a reasonable way. In the cyber physical systems and IoT world, security has become a major aspect for the design of new devices, mostly because of the continuous integration of IoT systems and cyber physical systems into industry and our daily lives. So, for example, considering keyless entry systems, these systems are usually a very, very likely victim for security attacks, because they are often performed in a cheap way using classical replay attacks. And one of the most prominent attacks reported in recent years was the Tesla Model S hack performed by a team at the KU Leuven, who were able to find out that the Tesla Model S was using a very weak 40-bit encryption key, and by using rainbow tables were able to easily find out what key material was used to secure the access to the car between the car and the key fob. So as these incidents are largely due to a lack of security considerations in the early system design phases, we wanted to come up with a framework which solves this problem. And considering related work, when we wanted to come up with this framework, we of course had to first consider security threat analysis, such as the well-known STRIDE analysis and the CIA triad, and also security risk assessment management, which is largely used in network security assessment and based on Bayesian attack graphs. So when we consider the design of embedded systems, there is a huge research field considering the design space exploration of feasible or optimal system solutions. And these classic design space exploration approaches consider power and performance of the system under design. There are also design space exploration frameworks which already integrate security aspects, but they are either integrated on a very abstract level, or the design space exploration frameworks focus on very specialized problems. So here we saw that there is a gap because none of these frameworks is able to give the designers a holistic view for security and together with classic non-functional requirements. So our security-driven design space exploration framework aims to close this gap. This framework introduces security constraints into the design space exploration based on security requirements and Bayesian attack graphs, and also considering security functionality and capabilities, and also the placement of secret key material. Furthermore, it adds the security performance, overhead and power consumption, and thus it enables the consideration of security aspects, but also the performance and the energy consumption induced by the usage of security mechanisms. So our framework is based on a classic design space exploration framework, which is publicly available. And our framework has 4 types of input views. One is the system behavior given as a task graph, the system architecture given as a graph of hardware components and bus systems. Then the attack graph, which describes the attack scenarios from the perspective of the attacker, and security functions, which also might use secret keys and are applicable by the design system to mitigate the attack scenarios. And the output then is a system partitioning and a task allocation, and also a selection of the security functions and their implementation by the security capabilities offered by the hardware components to mitigate the attack scenarios. And this leads then to the calculation or to the output of the security vulnerability, and also the system performance and the power consumption is one major output of the framework. So considering the task graph or the functional description, this is based on a task graph where the task operates on a set of data entities which come with certain security properties or requirements. And with this representation, we want to solve ambiguous behavior descriptions. Then we have the architectural view, where we have certain hardware components or processing elements, which come with security mechanism and implementation vulnerability risk. These modules are connected via communication buses. Then we also have the security functionality view, which basically describes what security functions are applicable by the system to mitigate possible attacks and to secure the properties of the data entities. And they also might use key material. Furthermore, both the security function and the key material might be aimed at by the attacker. And then we have the attack view, which is basically a Bayesian attack graph, where each node formalizes a step or a distinct attack step, aiming at one task in the task graph. And the probability on how likely the successful execution of one of those steps is depicted or is described in the conditional probability table. And in the end, we are interested in the unconditional success probability of the attacker reaching the attack goal. So when we want to map the tasks on the hardware components or processing elements we selected, we need to describe the implementation of the task on one of these processing elements or hardware components with worst case execution times. And second, the framework also makes sure that the tasks connected in the task graph are also reachable when they are finally mapped on the processing elements. So after this task mapping, or for each task mapping, the framework also makes sure that the security mapping is feasible. And this mapping contains two steps. So first of all, the framework makes sure by applying a rule set that each task is mapped to a processing element which is capable of executing or supporting the task security functions which the task uses to protect its security assets. These mappings must be fulfilled by all solutions. And then for each attack, the framework tries out different security functions and also tries out different key materials for these security functions. And using these security functions, the framework builds up different Bayesian attack graphs, extending the original Bayesian attack graph with which the attack scenarios have been described. And by doing so, each solution has a different vulnerability regarding a successful reaching of the attack goals by the attackers. And in the end, each solution must satisfy all attack goal thresholds, because the designer describes also each attack goal with a certain threshold, which must not be exceeded. So, considering an example mapping process, we have a task graph where each task is attacked by a distinct attack in the attack graph, and basically, depending on what task is mapped to which processing element, we have different assignment of the worst case execution time, but also a different selection of the security functions and the security capabilities implementing these functions. And coming with these different security functionalities, we add their attacks to the original attack graph. And thereby we constantly get different results for the unconditional attack success probability for the attack goal. So in this case, the goal would be A3, and the unconditional attack probability would be P from A3, which is calculated using the Bayesian chain rule. So for evaluation, we use the use case coming from our project partners, which describes a secure sensor system, which consists of sensor devices being placed in an industrial environment, communicating with a controller gateway, And this controller gateway is connected to an analysis server, which monitors the sensed data and performs, based on this sensed data, certain actions. The architecture of the sensor device contains a sensor, a microcontroller, and a secure element. The gateway is composed of a microcontroller and a secure element, and the analysis server is also using some kind of secure element, which might come from a hardware secure module, and some application processor, which can also be some microcontroller, which performs the analysis tasks. The potential attacks on the gateway, the server, and the sensor communication, and also the analysis server, was evaluated together with our project partners. And there are two variants of the use case. One where the gateway also opens the sensor data and pre-filters this sensor data before it is sent to the analysis server. And in the second use case, the gateway only forwards the packets. And basically, what we did was we fed these inputs into our framework. And what the framework produced us was a set of secure solutions, which are here presented in green color. So each dot here is one distinct solution, so one system partitioning and task allocation. And each comes with its own average attack success probability, which is just the average of all unconditional attack success probabilities of all attack goals for the attack scenario. And what we saw with the two variants, so what we can see here is that the best performing solutions are not the most secure ones, and that the overall solution space, which would have to be considered for system design, is largely reduced by using our the security requirements fed to our framework. And when considering the two use cases, we also saw that an unpacking at the gateway has an additional attack potential. So this means that more security mechanisms need to be in place, so that also the pre-filtering ring variant can be considered to be secure. So basically, the framework also outputs the secure and fastest variants or solutions for both use case variants. And here we can see that in use case 1, where we do a pre-filtering, a secure element with a higher security level has to be in place compared to use case 2, where the packets are simply forwarded. So based on this design space exploration, we also had a potential, or we proposed a potential realization of the system to our project partners, where we emphasized that the analyst server should be implemented in an HSM supported cloud solution. The sensor nodes and the gateway should be supported with a secure element. And the communication was realized using Bluetooth Low Energy between sensor and gateway, and Wi-Fi between gateway and server. So in the end, our framework allows the modeling of security attacks aspiration networks and to integrate them into the design space exploration of embedded systems or larger systems in general. And using our framework, designers can find secure solutions which are either performance or power optimal, and they can narrow the solution space which they will then need to consider in the end. The limitations are that the security attack scenarios the modeling of them is largely based on expert knowledge, and that there is unfortunately no general method for judging the security mitigation capabilities of certain hardware component. So in our study, we relied there mostly on common criteria certification and the usage of the common vulnerability scoring systems for the description of and the rating of attack scenarios. So I thank you very much for your attention, and I will happily answer your questions now.
Thank you so much, Lukas. Have we any questions in the audience? Feel free to pop them into our Q&A, and we'll present them to Lukas. Any questions at all? Oh wait, we have one here from Dr. Fadi here. So he asked, could you explain the meaning of the numbers in tables and graphs? I'm not sure if you could maybe clarify that question a little bit more.
So what's numbers exactly?
Yeah, Fadi, could you be a little bit more specific on the early tables? Do you want to pull them back up? So you don't have to remember.
I also have them here. So the early table. So do you mean the rule set for the mapping? So on slide, what is it? 7. So I don't know if you
Slide 8, he said.
Slide 8. Okay. So yes. So in these tables, there you capture the conditional probabilities of an attack step being successfully performed by the attacker. So basically, what you have in the left column is the state of the pre-setting attack steps. So, for example, for A1, there is, let's say, 0% of attack success probability if the first attack AX was not performed successfully, and it is has a chance of 40% to be successful if the pre-setting attack step has been performed successfully.